Hello, young math padawans. It's Mrs. Angel with your lesson for today on how do I factor this expression. So this is a mind map or a flow chart that I created last year to help my students kind of go through this process, almost like a checklist of if I just gave you a polynomial and I asked you to factor it, how would you actually know which of the methods to use? So we're going to start by just introducing this flow chart over here, kind of how to use it. And then we're actually going to use this flowchart when we go through and factor our expressions. So step one is always to look for a GCF, a greatest common factor among all terms. Whether or not there is a GCF, you would then move on to step two. So after you identify whether or not there is a greatest common factor, then you look at how many terms there are. There will either be 2 terms, 3 terms, or 4 terms in the expressions that we are factoring. If the expression is a binomial of 2 terms, it's either going to be a difference of 2 squares, which is our special case, or you're actually going to be done after you factor out the GCF. So binomials are pretty straightforward. On the other end of the spectrum here, if there's 4 terms, the only way we have to factor a 4-term polynomial is by grouping. Put in your groups, factor out your GCF, find your common. It's the trinomials, the 3-termed expressions, that are the most difficult to figure out. It all has to do with the leading coefficient. If there is no leading coefficient, there's no number out in front, that's pretty simple. You just have to use P's and Q's factoring. 2 numbers that add up to the middle term and multiply to the last term. However, if there is a leading coefficient, you either have to determine if it's a perfect square trinomial, one of those special cases, where the first and the last terms are perfect squares and that middle term is double their product, blah, blah, blah. Or we have to use our methods of supergrouping, slip and slide, or double cross, all of which are used to factor those trinomials. So the best way to use this flowchart is to go ahead and look at some expressions. So let's grab those notes and get started. Okay, so you should have a copy of these notes in front of you, either electronically or printed out. The cool thing about the electronic version of these notes is that there are hyperlinks that you can use. So consider this your little factoring toolbox. Here are all of the ways that we've learned to factor: GCF, grouping, supergrouping, etc. And if you click on those links, they'll take you to shorter videos that I've recorded in the past of those methods. And the longest video, I think, is 10 minutes. So it could just be a really quick review for you. The second link on this document is the How Do I Factor This Expression link. And that takes you to the flow chart that we just used that we're going to be going back and forth between. The third thing that I want to point out on this worksheet is how we are going to check on this page. We're actually not going to multiply to check anymore. We are going to evaluate to check. So let's go ahead and get started with expression number 1. So the first question we ask ourselves is, do these terms have a greatest common factor? Well, I see a 2m squared and a 10m, and I definitely know that 2 goes into both, potentially even something else. So yes, there is a greatest common factor here. Now, if the answer to that question is yes, your next step is to factor out that GCF, which I know you already know how to do. So go ahead and factor this binomial using GCF factoring now. Great, so you should have 2m times the quantity m plus 5. Now we look at what's left inside of the parentheses. So we still have a binomial inside of the parentheses, even though we factored out the GCF. And that's where we're now going to ask ourselves the next series of questions. So how many terms does that expression have inside parentheses? I see 2 terms. So this is a 2-termed binomial. So in my flow chart here, I'm looking at the yellow box. And it looks like if it's a binomial, I have to check if it's a difference of 2 squares. And if it's not, then I'm done. So let's take a look. First of all, is m plus 5 a difference? No. So that means this is not a difference of 2 squares. So our factoring method here was just normal GCF factoring, and I am done. This expression is fully factored. Now, to check our expression here and to show that the factored form, 2m times m plus 5, is equivalent to 2m squared plus 10m, we're actually going to evaluate. Evaluate means plug in a value in both expressions and see if they equal each other, because equivalent means same value. Now, I would like my life to be a little easy for this, so I'm going to plug in one of the easiest numbers in existence, and that number is 1. So I'm going to evaluate both expressions when m is 1 and see if they equal each other, and if they do, that means that my factored form is equivalent to the binomial that I started with. So here we go.
2 times 1 squared plus 10 times 1, well that's 2 times 1 which is 2, plus 10 times 1 which is 10.
So the expression has a value of 12. Let's go ahead and substitute 1 into the second expression.
2 times 1 times the group of 1 plus 5. Well, let's see, 2 times 1 is 2, 1 plus 5 is 6, and 2 times 6 is
12. So because these two expressions have the same value for the same variable, that means that this factored form is equivalent to this simplest form, and I know that I factored my expression correctly using GCF factoring. Let's take a look at number 3. Number 3 says x squared minus 10x plus 15. Step 1, GCF. I don't see a greatest common factor among x squared, 10x, and 16, so there is no GCF here. So we go ahead and move on to step 2. How many terms are there? I see 1, 2, 3 terms. So this is a trinomial with 3 terms. So now I'm looking at the green box in my diagram. So if the expression is a trinomial, it all has to do with the leading coefficient. If there isn't one, we can use P's and Q's. And if there is one, then we have to do one of these two methods. So let's look back there. As I look at this expression, I do not see a number out in front, meaning this does not have a leading coefficient. And trinomials without leading coefficients can only be factored using one method, P's and Q's. Two numbers that have a sum of negative 10 and a product of 16. Go ahead and factor this expression using P's and Q's now. Okay, so when I factored it, I ended up with the binomial x minus 8 times the binomial x minus 2. The order doesn't matter. You could have had x minus 2 first. Let's go ahead and evaluate to check. All right, again, I'm going to use what I consider to be the easiest number to check, aside from 0, which is 1. So I'm going to plug in 1 to both and see if they equal each other.
1 squared minus 10 times 1 plus 15. 1 squared is 1. 10 times 1 is 10 plus 15. That's negative 9 plus 15. And the first expression has a value of
7 when x is 1. Let's see if the second expression does as well.
1 minus 8 times 1 minus 2. 1 minus 8 is negative 7. 1 minus 2 is negative 1.
And the second expression also has a value of 7 when x is 1. So because these expressions have the same value for the same variable input, we know that they are equivalent. The only difference here is that one of them is written as a product in factored form, and the other one is written in simplest terms. Moving right along to number 5, 6x squared plus 54x minus 60. Step 1, look for a GCF. I do notice that there is a leading coefficient of 6, and I'm pretty positive 6 also goes into 54 and 60, so yes, there is a GCF here, and that GCF is going to be 6. Go ahead and factor out 6 from this trinomial now. Great. So now we continue to ask our questions, but we're looking at the remaining trinomial that's inside of parentheses. The 6 is still part of our product, but it's not going to affect how we factor going forward. So how many terms are inside the parentheses? I see 3. Which means this is a trinomial. The trinomial all has to do with the leading coefficient. Do you see a number out in front there, in front of that x squared? I don't, which means we are going to factor this using P's and Q's. Again, the 6 is part of the product, but it doesn't affect how we do this step. So go ahead and factor this expression now using P's and Q's. Find two numbers that have a sum of 9 and a product of negative 10. Okay, so I ended up with x plus 10 times x minus 1, and that 6 is still a factor out in front. Let's set up our evaluate to check. All right, just as before, I'm going to substitute in 1 for both expressions and see if they have the same value.
6 times 1 squared plus 54 times 1 minus 60, that's just 6, plus 54x minus 60, that's 60 minus 60, which is 0.
So the first expression has a value of 0. Let's see if the second expression does as well.
6 times 1 plus 10 times 1 minus 1, that's 6 times 11 times 0, that's 66 times 0.
And it appears that the second expression also has a value of 0 when x is 1, which tells me that my final answer is the equivalent product of the trinomial that we started with. Moving right along to number 7. First of all, is there a GCF among all 4 terms? I don't think so. No GCF here, which means we go on to step 2. How many terms are there in this expression? I count 4, which means we're looking in this area in our diagram. And as we mentioned, a 4-term polynomial can only be factored in one way. That's by grouping. So go ahead and factor this trinomial using grouping now. All right, so after I put in my group, factored out my GCF, and got my common binomial, I ended up with 5b squared minus 6 times 8b plus 3. I'm going to go ahead and set up my evaluate to check. And as always, I like to plug in 1. You could actually plug in anything you wanted, but I feel like 1 is pretty simple. So I'm going to go ahead and check.
40 times 1 cubed plus 15 times 1 third minus 48 times 1 minus 18. Well, that's going to be 40 plus 15 minus 48 minus 18. That's 55 minus 48 minus 18. That's 7 minus 18, or it appears negative 11.
I think my math is done correctly there. One way to find out. Let's check in the other one.
55 times 1 squared minus 6 times 8 times 1 plus 2. That's 5 minus 6 times 8 plus 2. That's negative 1 times 11. And the second expression also has a value of negative 11.
Which means that my factored form is equivalent to the 4-termed polynomial that we started with. Up next, number 9, 3n squared minus 19n plus 20. Do these 3 terms have a common factor? Nope, no GCF. So we go to the next question. How many terms does it have? 1, 2, 3. This is a trinomial. And trinomials all have to do with the leading coefficient. Oh no, there is a leading coefficient here. So that means we now have to figure out if this is a perfect square trinomial or not. A perfect square trinomial has a first term and a last term of perfect squares. 3n and 20 are not perfect squares, which means we're either going to factor this using supergrouping, double cross, or slip and slide. It's up to you which of the 3 methods you want to use. Go ahead and factor this using one of those 3 methods now. Okay, so I chose to factor this using slip and slide, but had you used supergrouping, you still should have ended up with your binomials of n minus 5 and 3n minus 4. Let me go ahead and set up my evaluate check. Here we go, evaluating both when n equals 1.
3 times 1 squared minus 19 times 1 plus 20 is 3 minus 19 plus 20, which is negative 16 plus 20, or 4.
So the first expression has a value of 4. On to the next.
1 minus 5 times 3 times 1 minus 4. That's negative 4 times 3 minus 4. That's negative 4 times negative 1.
And it looks like the second expression also has a value of 4, which means that this factored form, this product, is equivalent to the trinomial that we started with. Almost done, just 3 more to go. Number 11, 6m squared minus 28m plus 30. Is there a GCF here? You betcha. These 3 terms have a GCF of 2 in common. So start off by factoring out 2 from all 3 terms now. Great. Now what's left in parentheses is the trinomial 3m squared minus 14m plus 15. This has 3 terms, which means I'm looking at my green box here. Is there a leading coefficient? Yes. Is it a perfect square? I don't think 3 and 15 are perfect squares, which means just like the last example, it's up to us to choose supergrouping, double cross, or slip and slide. Pick the method of your choice and continue factoring this expression now. Great, so this time I chose to use supergrouping and I ended up with the binomials 3m minus 5 and m minus 3. I'm going to go ahead and set up my evaluate to check. Here we go.
6 times 1 squared minus 28 times 1 plus 30. That's 6 minus 28 plus 30. 6 minus 28 is negative 22 plus 30 is 8.
So it appears the first expression has a value of 8. Let's check the second expression.
3 times 1 minus 5 times 1 minus 2. That's 3 minus 5 times negative 2. That's negative 2 times negative 2, which is an expression of 4. So I made a mistake here.
Uh-oh, I made a mistake here. I got 8 in the first expression and 4 in the second. What did I do wrong? wait a second, what was the first thing we did? We factored out a GCF. I can't just leave that behind. That 2 is still part of my product, which means it needs to be part of my evaluation. If that 2 was a part of this, that's 2 times 4, which is an expression that has a value of 8. So it is super important that that GCF be a part of your final product. Now these both have an equivalent value, so I know that my factored form is equivalent to the trinomial I started with. Phew, I was freaking out there for a sec. Down to our final 2 problems. Number 13, 9x squared plus 24x plus 16. Is there a GCF here? Not amongst all 3 terms, no GCF. How many terms are there? I see 3, which means we're looking at our green box here. Is there a leading coefficient? Yep, that means we can't use our P's and Q's. Is it a perfect square trinomial? Let's find out. Is 9x squared a perfect square? Yes. Is 16 a perfect square? Yes. Okay, that means we get to test the middle term. So the square root of 9x squared is 3x, because 3x times 3x is 9x squared. And the square root of 16 is 4. So we're going to multiply these together and see if they add up to the middle term. 3x times 4 is 12x, and 12x plus 12x does equal 24x. So this is a perfect square trinomial. Go ahead and finish factoring this perfect square now. All right, I ended up with 3x plus 4 times 3x plus 4, or the binomial 3x plus 4 squared. Let's set up our evaluate to check. Here we go, evaluating when x equals 1.
9 times 1 squared plus 24 times 1 plus 16 is 9 plus 24 plus 16, which is 32 plus 16, or 49.
So the first expression has a value of 49. Let's check the second expression.
3 times 1 plus 4 squared. 3 plus 4 squared, 7 squared.
Also has a value of 49, so I know that this perfect square is equivalent to the trinomial that I started with. Last problem, 25x squared minus 1. Is there a GCF here? Not when 1 is one of the terms, definitely no GCF. How many terms are there? Only 2 this time. Interesting. That means we're working with the yellow box in our mind map. So if it's a binomial, either it can't be factored or it's a difference of 2 squares. Let's see if it's a difference of 2 squares. First of all, is it a difference? Yes. Does it have 2 terms? Yes. Are both terms perfect squares? Let's see. Square root of 25x squared is 5x, and the square root of 1 is 1. That means this is a difference of 2 squares. So go ahead and finish factoring this one now. All right, I ended up with 5x plus 1 times 5x minus 1. I'm going to set up my check. Let's see what they equal when x is 1.
25 times 1 squared minus 1 is 25 minus 1, or 24.
So the first expression has a value of 24. Let's check the second expression.
5 times 1 plus 1 times 5 times 1 minus 1. That's 5 plus 1 times 5 minus 1. 6 times 4 is also 24.
So because these expressions are equivalent, they have the same value for the same input, I can say that the product factored form is equivalent to the binomial we started with. And this concludes today's video. Again, this flowchart is a really important tool to have out while you're finishing the rest of your worksheet practice. And the even numbered problems are very similar in structure to the odd numbers that they're next to. That's it for today's lesson. I will see you next time.